Assalamu alaikum everyone. My name is Arfa Ashraf, roll number BSF 1702115. Topic Hydrothermal Synthesis, University of Education Township Campus, Lahore. Bismillahirrahmanirrahim. Key concepts of our topic are organic, inorganic, hybrid materials. Next, experimental methods, autoclaves, main factors governing the solvothermal crystal growth, nutrients in solvothermal crystal growth processes. Organic, inorganic, hybrid materials. Organic, inorganic, hybrid materials represent the interaction between two major branches of chemistry, organic and inorganic chemistry. One of these branches importantly contributes to the material sciences and have characteristic properties that induce various advantages and limitations. The most commonly used definition of these materials is the following. A hybrid material is a material that includes two moieties blended on the molecular scale. Commonly, one of these compounds is inorganic and the other one is organic in nature. The reason for developing hybrid material is to take the best properties of each component, of organic component and inorganic component, while eliminating their particular limitations and produce materials with new properties. Although the original birth of hybrid materials are not known exactly, the mixing of organic and inorganic components was carried out in ancient world, but at the end of 20th century and at the beginning of 21st century, hybrid materials attracted scientists' attention because of their availability of novel physiochemical characterization methods, and the field of nanosciences opened many points of view for approaches to new material. Organic, inorganic hybrid materials are simple to process and suitable to design on molecular scale. So, they can be applied in lots of branches of material chemistry with their different mechanical and characteristic properties. Chemical activity is the main property of hybrid materials. They bind the chemical activity of their constituents by exploring their ionic conductivity, selectivity, luminescence, electrical and optical properties, chemical or biochemical activity, which are used in selective membranes, batteries, sensors, electrochemical devices, electrochemical supercapacitors, supported catalysts, and photochemical energy conveyance cells. Hybrid materials can be classified by using their field of application or their chemical nature. Firstly, Judenstein classified the hybrid materials based on the interactions between organic and inorganic interface, and the selected interactions are illustrated in somewhere figure 1. This classification has two types, weak interactions and strong interactions. Weak interactions between two phases can be van der Waals, hydrogen bonding, or weak electrostatic interactions, and strong chemical interactions between the components. Although this is a simple classification, it helps the first prediction to categorize the complication of a wide variety of systems. Hybrid materials include a wide variety of organic and inorganic parts. Generally, inorganic parts involves transition metal oxides and p-block elements, and organic part involves organic diamine ligands. Organic component can affect the microstructure of inorganic oxide part by controlling the nucleation and growth of inorganic oxide. There is a synergistic interaction between two parts of hybrid materials. This gives the information about organic and inorganic nature. Additionally, more complex phases can be produced by a shift from thermodynamic to kinetic domain rather than equilibrium phases, and secondary metal complexes are used to cause more complex structures. These secondary metal complexes make bridges between the metal oxide and organic component that can bind directly to the metal oxide. There are various modes of involvement of organonitrogen components in metal oxide structure. These are space filling, structure directing, charge compensating, ligand bound to a secondary metal site, ligand bound directly to metal oxide structure, which are illustrated in somewhere figure 1. Here are some strength of interactions between organic and inorganic part. From moving bottom to top, the strength of interaction between organic and inorganic components are given. The van der Waals interaction is at bottom. It means it doesn't have more strength than hydrogen bonding, and next to the hydrogen bonding is ionic, and next to ionic is coordinative, and next to coordinative is covalent. It means covalent has higher strength of the interaction between organic and inorganic components. Here we are not discussing how the bond is strong, how the ionic bond is strong, how the covalent bond is strong. We are only considering the strength of interactions between organic and inorganic part. Generally, the inorganic part involves transition metal oxides or p-block elements, and organic part involves organic diamine ligands. Organic component can affect the microstructure of inorganic oxide by controlling the nucleation and the growth of inorganic oxide. There is a synergistic interaction between these two parts of hybrid materials. This gives the information about organic and inorganic structures. Additionally, more complex phases can be produced by a shift from thermodynamic to the kinetic domain. Rather than equilibrium phases, and secondary metal complexes are used to cause more complex structures. These secondary metal complexes make bridges between the metal oxides and organic components that can bind directly to the metal oxide. There are various modes of involvement of organonitrogen components in metal oxide structure that are discussed in the previous slide also. These are space filling, structure directing, charge compensating, ligand bound to a secondary metal site, ligand bound directly to metal oxide structure, which are illustrated in somewhere figure 2. Here is the figure 2. Different functions of organonitrogen components are given. In the top picture, that is labeled as A, showing the charge compensating cation, B, ligand bound directly to the metal oxide structure, ligand bound to a secondary metal site, and D, ligand that is on secondary metal bound to metal oxide structure, and E, bringing ligand between the secondary metal complexes. Experimental methods for hydrothermal synthesis are very simple. One of them is autoclaves. Through autoclaves we synthesize crystals and some other compounds also. First of all, we talk about the autoclave used as experimental method. Crystal synthesis and growth under hydrothermal conditions require a pressure vessel that is capable of containing highly corrosive solvent at high temperature and pressure. This suitable or ideal hydrothermal apparatus is autoclave. The first autoclave was made in Europe alone in 19th century and used worldwide in 20th century. An ideal autoclave for hydrothermal synthesis should include the following characteristics. First characteristic is inertness to the oxidizing agents, acids and bases. Next one is easy to operate and maintain. Third, a suitable size and shape to obtain a desired temperature gradient. Fourth, a leak proof with unlimited capabilities to the required pressure and temperature. And the fifth one is high mechanical strength to bear high pressure and temperature experiment for long duration. Autoclaves. The most successful material for autoclaves are corrosion resistant, high strength alloys such as stainless steel, iron, nickel, cobalt based superalloys, and titanium and its alloys. In some hydrothermal reactions, the reagent and solvents are non-corrosive and the reaction can take place in autoclaves directly. However, in most of the hydrothermal experiments, the reagent and the solvents are corrosive in nature. They can attack the vessel at high temperature and pressure. That's why it requires a suitable lining for inner walls of autoclaves. In order to grow high purity crystals in highly corrosive environment, Teflon beakers or liners are used. Teflon liner or beaker should sit exactly inside of the autoclave without leaving any space. Teflon is the most popularly used lining material, but it can't be used at more than 300 Celsius because Teflon dissociates, affecting the pH of unbuffered near neutral solutions above this temperature. In figure 2.1, stainless steel autoclave and its parts are given. An ideal hydrothermal autoclave should have the following characteristics. As we have discussed, inertness to the acid-basic and oxidizing agents. Second one, it should be easily assemble and disassemble. Third one, it should have sufficient length to obtain a desired temperature gradient. Number 4, it should be a leak proof at desired temperature and pressure. Number 5, it should bear high pressure and temperature for long durations of time. Here in this slide, the pictures are given of autoclave and the Teflon and the upper pressure plates, lower pressure plates, spring and corrosion discs that are used in autoclave experiments. And the second picture is showing the instrument that used to measure the pressure inside the autoclave. Here we move to the next slide. Main factors governing the solvothermal crystal growth: chemical factors, physical factors, kinetical factors. Chemical factors include nature of solvent, nature of nutrients, nature of seeds, the interaction of solvent with the walls of hydrothermal pressure vessel. Next one are the physical factors. Physical factors include the crystal growth temperature, the T value, the pressure value, the hydrodynamics in the crystal growth system. Kinetical factors. Kinetical factors may include the kinetics of dissolution, the kinetics characterizing the diffusion of chemical species, the crystal growth kinetics, the duration of crystal growth. Here we move to the next slide. Brief history of solvothermal crystal growth of large single crystals. The history of solvothermal crystal growth is closely related to the hydrothermal crystal growth of alpha-quartz due to its piezoelectric properties leading to the important applications, and its low temperature domain of stability is 573 Celsius, impeding the use of conventional crystal growth processes. The elaboration of alpha quartz single crystal was the first example for industrial development of hydrothermal crystal growth. Here are the pictures of diamonds, quartz, piezoelectric crystals are made by the hydrothermal method. New trends in solvothermal crystal growth processes. Solvothermal processes for growing large single crystal. Two different domains: crystal growth of oxides and crystal growth of non-oxides. Crystal growth of oxides include alpha quartz for its piezoelectric properties, aluminium phosphate, gallium phosphate, gallium arsenate. They also show the piezoelectric properties like alpha quartz. Next one is the calcite and The third one is zinc oxide with wide bandgap semiconductor, transparent, dielectric and piezoelectric properties. Crystalline aluminosilicates containing pores and cavities of molecular used as solvent catalyst and ion exchange materials. Some other examples of oxides that can be grown by the solvothermal processes are also given below, like potassium titanium oxygen phosphate oxide and hydroxyapatite, etc. Crystal growth of non-oxides. During these last years, strong efforts have been done for controlling the solvothermal crystal growth of gallium nitride using a process derived from the alpha quartz and the zinc oxide solvothermal crystal growth, and the reference is given below. Such efforts are supported by existing or potential applications of gallium nitride, like in optoelectronics, high frequency, high power electronics, and fast speed communication. The crystal growth of materials as nanoparticles. As the size is reduced to the nanometer range, the material exhibits specific properties due to quantization effects. In such a case, the morphology plays an important role: 0D, 1D and 2-dimensional. New trends in solvothermal crystal growth processes. Recently, one-dimensional nanostructure wires, rods and tubes have been the focus of intensive research owing to their applications in microscopic physics and the fabrication of nanoscale devices. The formation of a 1D nanostructure depends on two steps: the nucleation and the crystal growth. Here are the characteristics of the hydrothermal synthesis. Advantages of hydrothermal synthesis are given below. Most materials can be made soluble in proper solvent by heating and pressurizing the system close to its critical point. Number 2. Significant improvement in the chemical activity of the reactant. The possibility to replace the solid state synthesis and materials which may not be obtained via solid state reaction may be prepared through hydrothermal or solvothermal synthesis. Number 3. Products of intermediate state, metastable state and specific phase may be easily produced. Novel compounds of metastable state and other specific condensed states may be synthesized. Number 4. Easy and precise control of size, shape distribution and crystallinity of final product through adjusting the parameters like reaction temperature, reaction time, solvent type or surfactant type. Number 5. Substances which are low in melting point, high in vapor pressures and tend to go to pyrolysis will be obtained by hydrothermal synthesis. Characteristics of hydrothermal synthesis. Disadvantages of hydrothermal or solvothermal synthesis. Number 1. In this case, autoclaves can be expensive, and the second one is safety measures, safety issues during the reaction process, and the third one is impossibility of observing the reaction process black box, as we use the autoclaves for synthesizing crystal synthesis or hydrothermal synthesis, solvothermal synthesis. They are basically like black box because we can't observe any chemical or physical change taking place inside of the autoclaves. They are totally sealed and just act as black box and are unobservable changes inside of them. Next one are the applications. The hydrothermal method has been firstly proposed to stimulate the genetic condition of geological minerals. Later it has been adopted in the synthesis of molecular seeds and crystal growth. Now, with different starting materials, solvents, reaction temperature, as well as the other experimental parameters, people have reported the synthesis of various kinds of nanostructures through hydrothermal or solvothermal approaches, including metal oxide and carbonaceous nanostructures, and etc. Applications of hydrothermal synthesis in the preparation of nanomaterials. Number 1. Hydrothermal or solvothermal synthesis of zeolites. Next one is hydrothermal and solvothermal synthesis of metal oxides. Next, hydrothermal or solvothermal synthesis of carbonaceous materials, and hydrothermal or solvothermal synthesis of nanowires. Other strategies for the hydrothermal or solvothermal synthesis. This is the end of my presentation. I hope you like it. Allah Hafiz.